Everyone talks a lot about smart clothes, smart wearables, smart fibers, but to get to this adoption level of smart textiles, we need to find a fiber that's highly stretchable, highly conductive, and easily manufacturable all in one. In today's episode, we talk about a team from EPFL that takes inspiration from the manufacturing of fiber optics, or as Forbode like to mention, the manufacturing of different types of hard candies, to make this new stretchy electronic fiber that uses liquid metal and rubbery material, and they think they've solved the problem. Hey folks, on today's episode, we're talking about smart, stretchy fibers that can help track your every move, and they're made from liquid metal, which is really, really interesting and cool. But before we talk about this specific topic, I'm kind of going to jump to the end here, which is that you can use these flexible, smart fibers in stuff like wearables, in stuff like robotic skins, soft prosthetics, and even clothing if you weave them into long reels of fabric. And so that directly relates to a short message from our sponsor of today's episode, Mouser Electronics. We love Mouser because they're one of the world's largest electronic distributors, but they also have a lot of knowledge, a lot of expertise, a lot of connections with what's going on out there in the real world, what's being developed, and they write awesome technical resources on it, which we've linked one of these, which is an article titled "The Future of Healthcare May Reside in Your Smart Clothes." And it talks about how smart clothing using tiny sensors and special threads, such as the ones we're going to talk about during today's episode, can be used to help track health signs like your heart rate, your movement, and this can help doctors monitor patients from home. It can help you be a lot healthier with higher adherence, and you don't even have to be in the hospital or under constant monitoring to do that. It's a really interesting article, and I think it's an awesome application of one of these special stretchy electronic fibers that we're talking about today. So go check that out in the show notes as an awesome technical primer, but also kind of some technical context as to where this new development could lead.
Absolutely. And just to add more context, right? Is the idea of a smart fiber new?
No.
What has been, the field of smart fabrics? What are the limitations? Why doesn't my Under Armour undershirt have this already?
I'm not sure where you're going with this.
I'm just trying to say, what's the existing realm? What are the limitations? As far as I could dig, they were saying you can either have nice and stretchy clothes, which is what most of us are conditioned to have, right? Like your cotton shirts, they stretch to an extent. Your polyblend shirts, they stretch a lot. Or you can have a conductive one. There's this big drawback, this big balance of you can have either or. You can't kind of have both, right? That's the stage I was trying to set here.
Yeah, it's a great stage. I just wasn't picking up what you were putting down.
No, that's fair. I didn't do a good job of phrasing it.
But yeah, no, it's a great point, right?
Yeah.
Smart clothes and wearables that we want to use with fibers, they're great if they are conductive, but we also need those to be flexible, to be broadly applicable. And one of the interesting ways to do this is by using liquid metals, right? If you think about it, liquid is also very flexible and it's also very conductive, but it's been traditionally hard to use in small, stable fibers because if you think about it having like a vial of liquid metal somewhere in your shirt, if you bend that vial, the vial will snap and the liquid metal will spill everywhere. So most methods so far have struggled to mix high stretch, good conductivity, and easy manufacturing all in one. And that's something that really hits home for me is I just went and actually saw one of the newest, most exciting domestic textile plants inside the U.S.
Wow. Perfect timing.
Yeah, I know. A startup of our good friend Denver Rayburn called Framework. And they're working on some awesome stuff there that I wish I could share more about. But I will just say that this article got me really, really excited because I thought Denver could definitely use these fibers in some of his production processes and make some awesome, exciting, smart fibers. Well, this team from EPFL, just let's talk about the fiber that they're making and how they fixed these problems. Is they've just to rehash, it's been challenging to find one that's flexible, conductive, and easily manufacturable.
Right.
There's a team from EPFL that made stretchy electronic fibers, again, using liquid metal and a rubbery material. So it's stretchy, it's flexible, it's highly conductive. But one of the awesome things that they developed here is the way of also making it easily manufacturable on one. And the process that they use is called thermal drawing, which is used to make long, thin fibers. And I thought I had seen this before, and I wasn't sure, and then I saw that they mentioned it somewhere in the article. Is this actually the same process that's used to make fiber optic cables?
Right.
And I don't know if you've ever like watched how it's made video on YouTube on making fiber optic cables, but I have. And I thought it was super interesting that they make this thing called a draw, which is just like a chunk of material that loosely follows the basic structure of what they want the final fiber to look like, but it's usually a lot thicker and stouter. Like think about a puck the size of a hockey puck, and it's made of glass. And then the way that they turn that into thin fiber optic cables is they heat it up, and then they stretch it out really, 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 really long until it becomes thin and small. And they can usually, by controlling all the different parameters, get it to be a really consistent profile. They can get it to be flexible, and they can get it to make these like really, really long, really, really thin fibers. They use the same process called thermal drawing to create these long, thin fibers of rubbery material on the outside and liquid metal on the inside. So if you think about it, they started with their thermal draw puck, a chunk of rubber filled with this liquid metal on the inside, and then they heat it up and they stretch it out really, really long and thin. Well, it's rubbery and flexible and thin, just like a little tiny hose, but on the inside of that hose is all the liquid metal that used to be on the inside of that puck before they stretched it out. And these fibers, the end process is they're super stretchy. They're really, really good at sensing stretching, which is really interesting. There's something called the gauge factor, which I want to talk about in a little bit. And they're also stable over time. But if you think about it, super stretchy, stable over time, good at sensing different types of stretching, this makes it, or lends itself, really, really well to be used in something like smart wearables. The first application they use it in is a smart knee brace that tracks how the leg moves. But I think it's really interesting, this like preformed block filled with liquid metal. You heat it and stretch it into a long, thin fiber, and the pattern of liquid metal on the inside of that like rubber hose stays inside. And as it stretches out, these metal droplets can break and turn more conductive.
And correct me if I'm wrong, the amount of control you have in the original preform allows you to kind of map where in the thread you have conductivity, right?
Yeah, exactly. They can pick where the fiber's conductive versus non-conductive. They basically program the entire length of thread in this chunk of preform. They create a pattern inside this preform, and then they stretch it out. And just like fiber optics, it's pretty easy to make long, long, long lengths of really, really thin material, starting from a block of preform that's not that big. And it's awesome because it works like fiber optics. It's also probably pretty easy for them to scale up production of this material if it were to end up being used a lot in wearables and textiles.
It's funny hearing you ask, have you ever seen how stuff is made and how you watch the fiber optic one? Because where my mind went immediately, not having watched the fiber optic one, are those videos where they show you old candy makers making those tiny candies that have like a bunch of colors or designs in them, which starts off with like a big glob of hot candy that then goes through the form, gets stretched out, and then they control via temperature and whatever else to dye exactly what they want the final product to look like.
It's very similar. And like
shows you where our childhoods were focused on, me on my stomach, you on your mind.
Fair. But like glass, plastics, candies, they all behave actually very similar above a certain temperature.
Yeah.
And then you can heat them and stretch them into tiny fibers, and the pattern stays consistent inside.
Wonderful treats on the other side.
Yeah. No, that's a great example. That's probably more relatable than, have you seen how fiber optics are made? Yeah. I like that example a lot.
Anytime. But yeah, so you alluded to, God, why am I blanking? You said you were going to discuss. There we go, gauge factor. Boom. Talk about
really interesting. It's this factor that's meant to like watch how well changes in length in a material correlate to the change in electrical conductivity. So
Mhm.
it's like, how well, if I stretch this wire 50%, how much does the conductivity change? And what's the ratio between the change in length versus the change in conductivity? And that's like a good proxy for trying to say, how good is this thing at sensing stretch?
Right.
And so we have worked on something similar. There's a lot of stuff that we like run into where it's like, oh, we worked on something similar. We tried to create sensors that you could laser print on sheets of polymer and see how responsive they were to stretch. And one of the things we noticed is it was like moderately responsible to stretch. It wasn't enough that we could say this material would be used as a flexible stretch sensor, the gauge factor for stretching. It also wasn't stable enough that we would say it's completely inconsistent or completely consistent regardless of stretch. So we were actually in this like ugly middle area where it's like stretch does matter, but not enough for us to call this a stretch sensor.
Right.
But these fibers that EPFL developed, they're super stretchy and they're also super good at sensing stretch. So the gauge factor is 0.96. This basically just means the correlation between the change in length and the change in conductivity is 96%. So that's a pretty good factor in saying, like, if I stretch this 50%, this also means that the change in conductivity will be 50%. So this is super sensitive to changes in length, and it's in a stretch. So you can use this to do things like measure and detect the position of things. If you put in a smart knee brace, you can infer how long or what the angle of the knee brace is or the position of the knee based off of how long these materials, these stretchy fibers, are stretching. And in addition to this, it can stretch up to 9.2 times its length before it breaks. And it's also stable over time. So the electrical performance doesn't wear out over time as you stretch it and unstretch it and stretch it and unstretch it. This means that it is good for more than one use too.
That's the point that I was going to make. Is it really stood out to me that as a part of their test, they were like, the participant wearing the knee brace was jogging, squatting, etc., to make sure that it's going through like numerous cycles of stretching and unstretching to ensure that the electrical properties that they care about remain stable, and it did. So that's I don't know, really reassuring that something like this can find a place in consumer products, which again, we talk about a lot. It's cool when it's in the lab. It's cool when it has its applications, but it's even cooler when I can go buy it from my local Dick's store the next year or so.
Yeah, for sure. And they talked about a lot of the interesting options for this. Wearables like braces, sports gear, that's a really interesting application. That's where they've already used it.
Mm-hmm.
Another thing that's interesting is like soft prosthetics. You want to create somewhat of a feedback loop. That's like, if I have a prosthetic hand that's working around, can I use this as a proxy for like understanding the position of all of those joints and stuff like that? They said it could be woven into long rolls of fabric to make smart clothing, like what we talked about at the beginning of the episode, which is really interesting. But one of the things that I think is super interesting is less so than clothing, because then I think about like, how would I assume you need some sort of like microcontroller connected to all this to be able to measure the conductivity and then communicate that back to a phone or a wearable or something, something else that's like collecting the data and processing it. So in my mind, I'm like, well, I don't really want to like plug in my shirt every single day to my microcontroller. So maybe that's not as interesting. But one thing I thought was super interesting is they talked about using this for robotic skins, which is like, can we help robots get a sense of touch? Which I think is really, really interesting, is like, instead of trying to create an array of sensors all over the place, physical like touch sensors or stuff like that, can we use these skins with an array of these stretchy fibers in there? Can we use those as a proxy for the sense of touch on skin on a robot and basically allow these, lots of hype around humanoid or human-esque robots using this type of like smart skin, and these types of robots could potentially help them, if their material is slightly compliant and it's like a soft robotic hand, can we put a mesh of these fibers over the top of the skin so that it can tell when the compliant skin is budging and basically use that as a proxy for sense of touch? I think that's an interesting application where you're not concerned about like washing your shirt every single day and then having to put it on and plug it in. It's like these skins on these robots are already going to be instrumented and plugged in all the time.
That's a really good point, and it actually just made me think of these humanoid robot companies like Figure, Neo, I think even the Tesla Optimus. They've slowly started shifting from having hard exteriors to having knit exteriors. I wonder if they're also thinking the same thing or it's just a happy coincidence. But either way, um, it definitely does seem like the opportunity is there to just evolve the knit fabrics they're using to have this touch capable uh, material in there.
Yeah, and I mean I'm jumping several leaps in like technical capability here, but if you can use the length of these fibers to infer the position of a knee with a knee brace when someone's squatting or jogging, etc., it doesn't seem like too far of a leap to say, hey, if we've got a matrix of these and we know where they're positioned, can we also tell where there's a stimulus on the skin of this robot?
Agreed. It's a great idea.
I'm sure that's what a lot of these humanoid robot companies are working on, maybe already doing.
Maybe you just call them out and they're going to be upset hearing this. You just spoil the surprise.
I would love to see them use EPFL's stretchy conductive fibers as well, because it seems like they're pretty easily manufacturable, which is an important part of
And
this
if it
entire
does
equation.
happen, our audience is going to be the first to have gotten a snippet of it.
That's why you listen to the next bite, folks.
And that's why you make sure your friends listen to it too.
Yeah, friends, don't let friends miss an episode. That's what we say.
Amen to that. All right, you want to wrap it up?
Yep. Smart wearables and humanoid robots just took a huge level up. There's liquid metal fibers developed by EPFL that can stretch 9 times their size, but the important part is that they can sense every single move. They make it the same way you make candy or fiber optics, by heating and stretching a rubbery block called a preform filled with liquid metal. They stretch it out, and then the end result is these super stretchy, super accurate fibers that they've already tested in a smart knee brace to track motion. It's safe, it's flexible, and it's easily manufacturable. And that's why I think humanoid robots will never be the same after they get this fiber.
Boom. Fire.
Thanks, Tom.
Mic drop. All right. That's the pod.
All right. See you, everyone.